We're going to be proving the sine and cosine addition formulas. And to do that, we're going to look at these two angles down here. So we're going to look at the sine of alpha plus beta, or the cosine of alpha plus beta. And this we're going to accomplish by creating two right triangles, one that has this angle alpha, one that has this angle beta stacked on top here. So we have the adjacent side to beta as the hypotenuse of alpha. One other thing that's going to be important is that this point is on the unit circle. In other words, this radius here equals 1. And why do we want that? Well, let's take a look at the unit circle. When I have a point that's on the unit circle, its hypotenuse is 1, and so that makes some nice relationships. The x-coordinate of a point that's on the unit circle is just the cosine of the angle theta, and the vertical component here is just the sine of the angle. So we're going to be using these relationships in the figure that we're creating. So let's finish our construction and get the basic things. We want the vertical lines that are perpendicular to the base of this lower triangle. So we're going to create those. They're parallel to each other. So we have rectangles, and we're going to create the middle segment there. So we have that. It'll help show the relationships between the angles better. So now we're using the relationship I showed you on the previous figure, right? The radius here is 1, so this segment BC is just the sine of the angle beta, and the segment DB is just the cosine. So that's good. Now this one's a little harder to see, so this is what we're going for. We're looking at this relationship here. So let me step back and see if we can show where this calculation is coming from. Suppose that we call this segment AB. That's what we're trying to calculate. Let's just call it Y. It's a vertical segment, so for the moment we'll just call it Y. And then let's write this equation down, right? So we have, right, the sine of alpha equals Y over cosine beta. So we have the sine of alpha equals the fraction opposite over hypotenuse, right? So alpha equals Y over cosine beta. Okay, which hopefully will explain why we have this relationship over here. So, right, if I multiply through on both sides of this equation by cosine beta, then I have Y equals cosine beta sine alpha. And so let me clear off the pen here, and you can see that we have this nice relationship over here proven. Okay, so this segment is AB is cosine B sine alpha, and I have a rectangle here, so this red segment is also equal to the same quantity. So now we need to show that all of these angles are similar, or excuse me, are congruent, right? So alpha and theta, alternate interior angles. Then we also have alternate interior angles between phi and alpha prime, and both phi and alpha prime are complementary to angle FBC, right? This right angle, excuse me, this angle here. Let me back this off so we can see. This angle FBC is here. And so all these angles that are shaded red or pink, whatever color you're seeing, are congruent. Okay, so that'll be important. Now we're going to argue that sine beta cosine alpha is the length of this green segment. Okay, Do the same thing that we did before. If you just write what the cosine of alpha prime is, right, you can solve for it because we know already that this is sine beta. So you can do an equation just like we did down here. I'll leave that one for you. And then the final step is to realize what it is we're looking for. We were searching for, well, one thing we were searching for is the cosine. Well, the cosine of alpha plus beta, remember the hypotenuse of beta, this point C is on the unit circle, so this equals 1. So we're in the situation where this line segment we're looking for down here, the length of this line segment, dg, is equal to the red plus the green segments here, right? Well, we know that the segment CF is sine beta cosine alpha. That's this one, sine beta cosine alpha. And then the red ones, since they're two congruent sides of this rectangle, we know that FG is cosine beta sine alpha. And that gives us the formula for the sine. I'm sorry, I drew the wrong segment. The segment we were looking at. The one I drew was for the cosine, so that's the one that's not shown. So we could do cosine of alpha plus beta, and I'm not going to write this formula out, but that's the one that corresponds to the segment down here. The sine corresponds to this segment here, which is the one that we showed the calculations for to arrive here. So there's some extra work to do to understand how both of these formulas arise, the sine and the cosine. Also, there is a way to use this same figure to prove the subtraction formulas. And let me just quickly show you that. Right, so if I want a cosine or sine formula for alpha minus beta, then what I have to do is I have to make the entire angle alpha and then choose a smaller portion of it, say, to be beta. Right? But all of these relationships still exist, so I should be able to get an expression for the sine of alpha minus beta or the cosine of alpha minus beta in terms of these different sides, right? We can calculate what that should be. So you should definitely go through all the details so that you can prove the sine and cosine addition formulas and also be able to prove a subtraction formula for both sine and cosine. One final point is we can also get double angle formulas, right? How do we do that? Well, we just set, maybe I should have written this differently. To do a double angle formula, we set beta equal to alpha. And then we can substitute into an addition formula and we can get the double angle formula. So this single figure is going to allow us to not only do addition formulas, subtraction formulas, we also get the double angle formulas. So it's a very important construction to know.